we left off here on chapter 16. We were just going through all the reactions, and that's all chapter 16 is, memorizing all the reactions with aldehydes and ketones. So in this case, we're given an aldehyde and then this specific molecule. So this specific molecule is called your hydroxylamine. I don't know if that's important, but just a note. But the point is, whenever you have an aldehyde or ketone plus a hydroxylamine, you do the same thing you usually do. So you cut off the H2, you cut off the O, and then you take the N whatever and put it where the oxygen used to be. So in your final product, you get this thing. And then this functional group is called your oxime. I also don't know if that's important, but just in case. So hydroxylamine plus aldehyde or ketone gives you your oxime. And then next you got a ketone again, but in this case, we're giving it this H2N NH2. So the H2N NH2, if you remember, is called a hydrazine. So when you give a ketone or aldehyde hydrazine, they react together and form a hydrazone. So it's the same thing, cut off the O, cut off 2 hydrogens, copy and paste. And then this functional group, the double bonded N with the NH2, that is a hydrazone. But one thing you have to be careful with hydrazines and ketones, if you have like a ketone and then you give it hydrazine, but on the bottom there's more reagents like KOH or H2O, what happens here is a Wolff-Kishner reduction. So if we did have KOH and H2O on the bottom, all we would do is cut the ketone off. But we don't have that, and we just have hydrazine. So it's gonna like do the copying and pasting and turn into a hydrazone. The product would literally be the same thing with just no ketone. So that. Okay, so next, whenever you see this PPH3 or like a phosphorus attached to a bunch of oxygens, like this, you know it's either a Wittig or a Horner-Wadsworth-Emmons. The only thing it's different between the two is like the stuff that's attached to the phosphorus. But they do the exact same thing. Like the final result is going to be the same. So for Wittigs, this first step where I'm giving you PPH3 and an alkyl halide plus a base, that is going to be the ylide formation step. So to get a complete like Wittig or Horner-Wadsworth-Emmons reaction, you need an ylide or a phosphonate ester, and then you also need an aldehyde or ketone. So we already have our ketone here, but we don't have an active ylide yet. So we need to make that. So the way that ylide is made, you take your PPH3, the phosphorus is a good nucleophile, so it goes in, attacks the alkyl halide, and then the chlorine goes away. So now you have the same thing, except the phosphorus is attached to an R group now. So this would be like the inactive ylide. This is inactive because if you remember the square transition state, there's no like nucleophilic part of this. So what we need to do is go in with a base. In this case, we have NaH. the base is going to deprotonate the carbon adjacent to the phosphorus. So the NaH goes in, deprotonates there, and then you get a double bond or an active ylide. So from this reaction, this now becomes a double bond. Technically, it's a lone pair on the carbon, but by resonance, it can jump down and make a double bond. And then after that, you're good to go. So this is your active ylide. So once you have your active ylide, you can go ahead and just cut and paste. So what I do here, I cut off the oxygen of the aldehyde or ketone, and then I cut off like everything from the phosphorus. So I only focus on the R groups that are attached here. So like the carbon bonded to the phosphorus and the stuff attached to that carbon. And then all I do is take the stuff like I highlighted in pink, the carbon attached to the phosphorus and all the R groups attached to that carbon. And then I paste it where the oxygen used to be. So we retain the double bond of the carbonyl. The only thing that's different is this new R group replacing the O. And that's what both Wittig and Horner-Wadsworth-Emmons do. But the thing is, you have to make sure you have your active ylide. Otherwise, it's not going to react with the aldehyde or ketone. And you need to have some kind of base to deprotonate it to make it active. All right, so for like retrosynthesis, you basically just need to look at the alkene and then cut it in the middle. So from the alkene, so the way I got the ylide product was cutting off the oxygen of the carbonyl. So here I would just look at one end of the double bond, either one, it doesn't like matter in this case. And I would just get rid of the R group on it. So I would like detach this R group and then put an oxygen right on this carbon because that's how I got the final product. So I'm assuming that this was the aldehyde we used, and then this with the phosphorus thing was like the R group that we used to replace the oxygen. So I know that this was going to be like either the phosphonate ester of the Horner-Wadsworth-Emmons or the PPH3. But it says HWE in the question, so let's stick with that. So all I did was like remove one of the R groups, put the oxygen back onto the double bond, and then separate it to find like the phosphorus thing. Victoria, you had a question?
Yes. So for example, this is a symmetrical alkene. Would it matter like if it was an asymmetrical, which side the alide is the one that we're using, or the aldehyde or ketone, or it doesn't matter at all? It will give the same product.
It doesn't matter. As long as you have like a side that would give you the correct product, like you can do it either way. It doesn't matter.
Okay, awesome. Thank you.
Okay, so now that we've identified the ester that we used and the aldehyde or ketone, we can go ahead and draw the transition state. So the transition state of these reactions are just a giant square, basically. So what I do, I take the aldehyde and I line up the oxygen with the phosphorus. And then the phosphorus is here. It's got all its O's sticking out. And then I have the R group of the phosphorus ylide. So I line those up. I line the carbonyl carbon and then the phosphorus carbon together. And so now what happens is that the carbon of the phosphorus thing attacks the carbonyl. That becomes a single bond. And then the oxygen of the carbonyl attacks the phosphorus. So you get like a square thing. So you have these new bonds. But one very important thing that you will probably get tested on is the stereochemistry of these R groups in the transition state. So when you're doing these reactions, the major product of the alkene is the transalkene, the E alkene. So in order to get that in the transition state, the R group substituents have to be trans to each other. So the two methyls up here are going to be trans. So I'm going to make one wedged and I'm going to make the other one dashed. And then this would be the accurate transition state. But the real important thing is this. Keep that in mind. And then if you have more substituents, like if these carbons have multiple R groups or like one more R group on them, the biggest ones are going to be trans to each other still.
So the product is always going to be trans. That's what you're saying.
Yes, and that means the transition state is always trans as well.
Okay, awesome.
Okay, so yeah, that's it. For Horner, Wadsworth, Emmons, and Wittig, just keep in mind the copying and pasting you have to do, and then also keep in mind the transition state, what that looks like, and that should be it. But next we have this reaction, which is Bayer-Villiger oxidation. So MCPBA does two things. MCPBA can epoxidate alkenes, or it can oxidize aldehydes and ketones. So in this case, we have an aldehyde, and you have to keep in mind the order of like preference. So what MCPBA does is that it inserts an oxygen in between the carbonyl carbon and then something else that's next to it. So in this case, we have a hydrogen and then a phenyl. So the MCPBA is going to insert an oxygen between either the hydrogen or the phenyl. So you have to decide like which side it's going to insert on. For that, you have to keep in mind like the order of preference, I guess. So for Bayer-Villiger oxidation, you're going to prefer to insert the oxygen between a hydrogen, then a phenyl, and then like a tertiary, then secondary, then primary alkene. In this case, the top priority is the hydrogen, and there's a hydrogen on the aldehydes. So we're just going to go ahead and stick the oxygen in there. So just memorize that like aldehyde plus MCPBA equals carboxylic acid. And then over here, we have MCPBA and this ketone. So right next to the carbonyl carbon, we have this carbon and this carbon. The one on the left is more substituted, so it's going to prefer to insert between the carbonyl carbon and the more substituted one. So we're just going to go from a 4-membered ring to a 5-membered ring with an oxygen in the middle now. And then you just kind of push this thing just one more bond over. So the next one is another oxidation. With this one, I think I told you that it goes to a carboxylic acid. It does if you have an acid workup, but I think Dr. Roche like specifies with an acid workup versus without. So if you just have these reagents plus an aldehyde, it's going to go to a carboxylate ion. So yeah, you just got to memorize that. I think the same thing happens with like AgE2O. Anything with silver is going to turn it into the carboxylate. Okay, so moving on to chapter 17. Chapter 17, one thing to keep in mind is the order of reactivity of all the carboxylic acid derivatives. So for this chapter, all we're doing is basically just substituting the leaving groups of all these carboxylic acid derivatives. So the reactivity of a carbonyl is determined by like how good of a leaving group it has. So chlorine is the best leaving group, so it's the most reactive. And then your acid anhydride, the leaving group is this thing, which is pretty stable, so it's the next reactive. And then your esters and carboxylic acids, the leaving group is the alcohol and like the OH. So that's like practically the same. So those have the same reactivity. And then the very worst leaving group is the NH2. So it is the least reactive. And the other thing you need to keep in mind is like the ease of reactivity. So it's much easier to react going from more reactive to less reactive. So like it's very easy going from an acyl chloride to an amide, but going from an amide to like an ester is very, very difficult and will give you just terrible yields. So you don't really go like upstream of this order. And chapter 17 seems like a lot of reactions, but it's really very simple. And besides these two up here, they can be summarized very easily in these pretty little charts. But for the first two reactions, the very first one going from carboxylic acid to acid halide, we've seen like 500 times and everyone knows it. You're just going to use your Sockle. So Sockle 2 does this transformation from carboxylic acid to acid halide. And then the next one is to make an acid anhydride. So if you have a dicarboxylic acid, like just carboxylic acid on either end, what can happen when you give it heat is that you'll have an H2O leave as a water, and then one of the oxygens is going to like attach itself to the other carbonyl. So you're like condensing it with the loss of water, if that makes sense. All I just like do a nucleophilic attack from this and then the water leaves as a leaving group. So in the final product, I have this. We get a cyclic acid anhydride. And then keep in mind, you can use this acid anhydride for a bunch of stuff. So you can use it for like chapter 18 and 19 for acylations. You can use it for Friedel-Crafts acylation. So he likes that one for multi-step problems. Yep, the reagent's heat. So besides those, we can summarize everything like this. So for the very first square, it's like going from all the derivatives to a carboxylic acid. So like if we look up here, carboxylic acid is not very reactive. So we can go from all of these derivatives and react it with the same nucleophile and get to a carboxylic acid. So that's why like the reactions of the chapter are so convenient. So all we need to do is give another derivative H2O. So if we give an acid chloride H2O, it's going to give us a carboxylic acid because it's just going to go ahead and attack, get rid of the chlorine, and then substitute an OH there. Same with the acid anhydride, H2O gives you a carboxylic acid. The ester is a little different. If you give the ester water, it will turn into a carboxylic acid, but you do need some kind of like acid catalyst. The other way to do this, the other way to go from esters to carboxylic acids is by using like a stronger nucleophile than water. So what happens a lot of the time is this. So you're going to have NaOH and H2O over H3O plus. And like you'll see those reagents being used. Actually, let me just make the actual arrow of that. So this is the most common way for ester hydrolysis. And then going from a bromine to a carboxylic acid, you do that via a Grignard. So the very first step is to give it magnesium and then carbon dioxide. So it mixes with the magnesium, forms a Grignard, and then attacks the carbon dioxide. And then you get a carboxylic acid. And then for the esters, same idea, except now the nucleophile you're using is a little different. So in the end, we're substituting for this OR group. So the nucleophile we need to use is an alcohol. So in this case, it's an OMe. So we're just going to use methanol for all these nucleophiles. So for the acid chloride, we give it methanol, it turns into an ester. For the acid anhydride, same thing. And the carboxylic acid, it's the same thing, except you would need an acid catalyst because they have similar reactivities. So an acid catalyst makes the reaction a lot easier. And then amides are the easiest because you can go from all the other derivatives to an amide because it's the least reactive. And then to do that, you just give it NH whatever. So in this case, we end with an NH2 attached to the carbonyl, which means our nucleophile was an NH3. So you can see with like all these other reactions, like we lost a proton during the substitution. So I think about it like the proton from the nucleophile like transferred to the leaving group. So when you're doing retrosynthesis to find the nucleophile, I just find like what was substituted at this position and then add a hydrogen to it, and then that's a pretty safe way to get it. So for all these, it's NH3. For the amides, you can use a primary amine, secondary amine, just primary and secondary amine, or NH3 as the nucleophile. So NH3, NH3, also NH3, and yeah. So that's chapter 17. That's really all you need to know. All these reactions plus the order of reactivity. I don't even think like the order of reactivity is that important, but like sometimes it's just a test question. Like I'll just ask you for the order. But yeah, let's move on. So now with chapter 18 and 19, we're no longer concerned with the carbonyl carbon. We're concerned with the reactivity of the alpha carbon. So on a carbonyl, the carbonyl carbon, let's say it's number 1, the adjacent carbon is going to be carbon alpha. And then the protons on carbon alpha are kind of acidic because they're resonance stabilized. So when we deprotonate those alpha carbons with a base, you get your enol or enolate. So for the first one, if we're using a base to get the enolate, this is what happens. So the base goes in, takes the proton, the electrons from the proton carbon bond go up to form a double bond, and then this pi bond goes up because you can't have 5 bonds on one carbon. So now you have this alkoxide ion with a new double bond. And then this is called your enolate. It's the enol-8 because it's an ion. If we're using an acid, it's a little different. So with the acid, oh, oops, that should be a 3. The first thing that happens with an acid, it protonates, the oxygen of the carbonyl protonates itself. And then it becomes positively charged. So, and then the same thing happens, the same alpha hydrogen elimination. So once that protonation happens, we can go in with the nucleophiles or the conjugate base and then do the elimination. You form a new double bond, these electrons go up. So instead of an alkoxide this time, you have an alcohol. So you have the alcohol and then your alkene. So this is your enol. So we skip the enolate and then went straight to the enol form. And then the keto and enol forms are at equilibrium in solution. Like it's just going between enol and keto. But now that you have this double bond, so this double bond can also be represented like this. Actually, let me do it with the base catalyzed. This can also be represented by this as a resonance form. So we can bring the electrons from this lone pair down and then this pi bond onto the carbon. So essentially what we have here is a delta negative or a lone pair on the alpha carbon. So that means the alpha carbon is now a really good nucleophile. So because it's a really good nucleophile, we can just give it a bunch of electrophiles and it's going to attack the electrophiles. So we can just add a bunch of stuff onto the alpha carbon, and that's chapter 18 and 19. It's just deprotonation and then adding stuff where you deprotonated. Okay, so for this, when you go from the keto form like this, I told you that the keto and enol forms are at equilibrium in solution. So that means that you're going from keto to enol back to keto. So what happens when you start with a chiral center? In this case, we have a chiral center at the alpha carbon. This carbon is attached to 4 different groups. Let's say that this methyl is wedged. So we have, I don't know, either an R or S carbon. What happens in base when you form the enolate, it goes through that double bond intermediate. So the enolate, you have a double bond on the alpha carbon. When you have a double bond, everything, everything is planar. There's no more chirality. This methyl is now planar. So now what happens when you reprotonate it to go back to the enol form? You also restore chirality. But the thing is, you don't get to choose which chirality you restore. So you could bring it back as either R or S. You don't pick. So it's a 50-50 mix. So this happens. This is a chiral center and it's racemic. The other thing to note here, we are using D2O, so we're using deuterated solvent and nucleophile. So in the final, whenever you see this deuterated stuff in the final product, like when you reprotonate the enolate to go back to the enol, you should just know that there's also a deuterium sticking out of it. So to that alpha carbon, it's now racemic, and then you added a hydrogen back, or in this case, you have to be wary of the hydrogen isotope. So the methyl and deuterium are going to be switching as wedged or dashed, and you'll get your racemic mixture based on that. But yeah, so the criteria for racemization is having a chiral center at the alpha carbon, and then also having a hydrogen that you can deprotonate. Because remember, you can't form the enol if you have no hydrogens to eliminate. So yeah, chiral center and one alpha hydrogen. That's what you need. And then basic solution to get a racemic mixture. Okay. So when you're forming an enolate, you're not always going to get asymmetric ketone. So on a ketone, you have two alpha carbons. So you have to pick which side you're going to deprotonate from. And then you can change which side is the major like enol, depending on what base you use. So the kinetic enolate is formed by deprotonating at the least hindered carbon. So this carbon is just a CH3. There's not much steric hindrance, so a base can easily go in and deprotonate those carbons. So to form the kinetic enolate over here, we're going to use some kind of bulky base. So if we use something like our LDA or LIH-MDS, they're very sterically hindered, so they're going to go for the easiest carbon. So a bulky base takes you to kinetic. And then a smaller base takes you to thermodynamic. This is thermodynamic because it's more stable, and stability is determined by how substituted the alkene is. So this alkene is tetrasubstituted. This one is disubstituted. The tetrasubstituted one is far more stable, so it's thermo. And then the reagents you use for this, any base that has like an O minus basically. So NaOET or like NaOH.
How did you determine the first one was kinetic again? I'm sorry, because it was bulky.
The first one is kinetic. Well, not because we used a bulky base. It was kinetic because it forms faster. And it forms faster because it's easier for a base to deprotonate on the less hindered side.
Okay, thank you.
All right, so now that we've formed our enolate, we can go ahead and attack electrophiles with it or substitute at the alpha carbon. So there's a few like categories of reactions. The first one is halogenations. So in this specific reaction, you're gonna have like a carboxylic acid and then these reagents. So you're gonna have a carboxylic acid, a protecting group, and then like an X2, usually Cl2 or Br2. So protecting group, like halogen protecting group, like SOCL or SOBr, and then your Cl2 or Br2, you know it's going to be your Hell-Vollard-Zelinsky reaction. So this is your HVZ. The point of an HVZ is to get a carboxylic acid that's halogenated at the alpha carbon. So all we do in the end product is add whatever halogen onto the alpha carbon. So the very first step of this reaction, we're giving it Stockl. So we know the OH turns into a Cl. Next, so this I guess spontaneously turns into the enolate, but the alpha carbon now attacks one of the Cls, and then you just protonate at the not protonate, halogenate at the alpha carbon. So after this step, the enol equivalent of this molecule attacks one of the Cls. So we get one more chlorine on there. And then the final step with the H2O, all it does is restore this halogen back into a water. So it turns the acyl halide into a carboxylic acid again. Then this chlorine remains. So all we did was halogenate at this position. Then one thing, I don't think he ever cared about this, but if you just stopped at after Cl2 and didn't do water, you would get this product that's dihalogenated. And then the other halogenation reaction you can do is the haloform. So whenever you see a carbonyl and then these reagents, so X2 and then base and 3 equivalents of it, you know it's haloform. So with the haloform, you go from a ketone or aldehyde, and then go to, I think just ketone. You go from a ketone to a carboxylate ion plus a haloform functional group. So that happens like this. So with the first step, when you're halogenating it, you always have a methyl here for haloform. The methyl has 3 hydrogens. During the reaction, each hydrogen gets replaced by the halogen. So in this case, we have I2. So I'm going to replace all the hydrogens with iodines. So this carbon now is attached to 3 iodines. Because there's so many halogens attached to one leaving group, this carbon becomes a very stable leaving group. I already said leaving group. Because there's 3 halogens attached to the carbon, it's now a really good leaving group. So then we go in with the base again, and we attack the carbonyl carbon. And then your carbon attached to the 3 iodines just hops off. So now we get our carboxylate ion. Plus our methyl with 3 halogens attached to it. The CHI3, this is the haloform.
Why is it an oxygen at the end and not an OH?
I guess because there's nothing to protonate it, but if you did acid workup, I'm sure you would get an OH. If it's in basic conditions, you get carboxylate.
The CHI3 is the haloform?
Mm-hmm. Okay. So now, to do alkylation, all we do is give the enol or enolate an alkyl halide. So your alkyl halide, those are electrophilic. So it's really easy for the enolate to just go ahead and attack from the alpha carbon. So for this, the very first step is base. So NaOET, ETOH, whenever you see a base and then your carbonyl, you know you're going to deprotonate at the alpha carbon. So in this case, it's NaOET. So I'm going to prefer the thermodynamic enolate. There's two sides which I could deprotonate at, but I'm going to deprotonate on this side because it would give me the more stable alkene. It would be tri-substituted. So I'm going to express the enolate just like this. You can draw it as a lone pair or, oops, as a double bond. Now that I have this nucleophilic carbon, I'm just going to go ahead and attack whatever electrophile there is in solution. So in this case, we have methyl iodide. So I attack the carbon, the iodine leaves, and then we just get a methyl substituted onto the alpha carbon. And that's it. We just alkylated the alpha carbon. So now I give you LDA and this like benzyl iodide. So LDA I know is a base, so it's just going to go ahead and deprotonate. There's only one alpha carbon with free hydrogens on it, so there's only one option to deprotonate on. So I'm going to make the enol. Can alkylation happen with acid? I don't see why not. I've just never seen it done with acid. So yeah, I never saw it, so I didn't like think to put it as an example. But maybe there's a reason I never saw it. But anyways, what happens here is that the deprotonated alpha carbon, good nucleophile, goes ahead and attacks the alkyl group next to the halogen. So it's just going to go ahead and attack the CH2, the I leaves, and then we just get that substituted onto the ester. So once again, we just alkylated the alpha carbon, and that's all. So there's some other stuff you can do with beta dicarbonyls. So the first beta dicarbonyl, well, it's called a beta dicarbonyl because when you have your carbonyl, remember the carbonyl carbon is 1, the next carbon over is alpha, and then the carbon after alpha is beta. So there's a carbonyl here. On carbon beta, there's another carbonyl, so it's a beta dicarbonyl. But anyways, there's two synthetically useful beta dicarbonyls. The first one is this one, the acetoacetic ester. That's the name of this molecule right here. And then the one on the bottom is called your malonic ester. So what I recognize with acetoacetic ester, I know that in the end, this ester portion of it is going to leave. And then I'm going to have stuff added onto this alpha carbon. And then I look in the reagents to see what stuff I'm adding to the alpha carbon. For malonic ester, I know that in the end result, one of the ester sides gets cut off. And then in the end, I'm ending with a carboxylic acid that's substituted at the alpha carbon. So in here, there's like some just random stuff attached to it. But it's important to keep in mind that like with the acetic ester, you end with a substituted ketone. If you're starting with malonic ester, you end with a substituted carboxylic acid. But let's just take it step by step. So for acetoacetic ester, the first step we have is NaOET. That's going to give you the thermodynamic enolate. So it deprotonates right here. And then once we have our deprotonated carbon, good nucleophile, so it attacks any alkyl halide. So in the solution, we have ethyl bromide. So we can go ahead and attack the ethyl and then get rid of the bromide, and then substitute that on. The H2O is just there for like protonation purposes. It's just a workup, doesn't really do anything. The important bit is that we just added an ethyl onto the alpha carbon. But on the alpha carbon, we still have one more hydrogen. If we are left with hydrogens on the alpha carbon and we want to alkylate it again, we can do that. The only thing that changes is the base. So for the first alkylation, you use NaOET. For the second one, you use tert butoxide. So in this case, it's the exact same idea. The tert butoxide deprotonates the alpha carbon. You get your enolate again. The enolate just goes ahead and attacks the alkyl halide. Now you get 2 substitutions on the alpha carbon. So we still have our ethyl, and then now we have this new thing. The very last steps of this, of your acetoacetic ester or malonic ester synthesis, is the hydrolysis and decarboxylation. So in the last steps, you hydrolyze the ester using these reagents. And then these reagents down here are for decarboxylation. So when we hydrolyze this ester turns into a carboxylic acid, so it becomes an OH. And then with the reagents down here, it's decarboxylation, so we can just go ahead and cut off the carboxylic acid that we just made. So after the top reagents, we get this molecule. And then if we react it with the lithium hydroxide and DMSO, we get our final product, the substituted ketone. Would tert butoxide be too bulky? Probably. I'm not really sure why they use tert butoxide as the second base. So I don't have an answer for why that's used instead. I would actually agree with you, but I never looked into it. So end product, disubstituted ketone at the alpha carbon. Let's see, for the malonic ester, it's the same idea. So the very first step, you have a base, so you deprotonate with the base. And then the next step, you attack the alkyl halide you have in solution. So we attack the methyl iodide, and then we've just substituted the alpha carbon with a methyl. And then we're not doing a second addition this time. So we go straight to decarboxylation. So after the first step, the esters get turned into carboxylic acids. After the second step with the lithium hydroxide, it gets decarboxylated, but only one of the carboxyls leaves. So let's say this one goes. and then you're left with a substituted carboxylic acid.
What does the very first step do? The NaOET, ETOH.
It deprotonates. So like I said, every time you have a carbonyl and a base, the base is going to deprotonate at the alpha carbon. So it just forms the enolate. All right, let's see. So chapter 19, same idea, deprotonate the alpha carbon. In the case where LAOH wasn't there, like, would you form the enolate again? I don't think so. I think you just like end here as the product. But chapter 19 is the exact same idea. Deprotonate, form an enolate, and then attack other stuff. So the very first reaction of chapter 19, I wouldn't like try to categorize each of these reactions of 18 and 19. Like starting from chapter 17 onwards, I wouldn't think like, oh, this is so and so reaction, so it's this. Except for like a few like haloform or whatever. I would just like look at it and then take it step by step. So I see that there's 2 moles of this ester in solution, and I see it's being reacted with base. I know base deprotonates carbonyls. So I'd be like, okay, base is going to deprotonate 1 equivalent of this ester, and then that is going to attack another molecule of the ester because carbonyls are electrophilic. So let's do that. So the very first step is base. We're going to deprotonate it at the alpha carbon and get our enolate that's nucleophilic. Then there's 2 moles of that in solution. So we take another equivalent of it and it gets attacked by the alpha carbon. And then it has an OET leaving group. So it's going to attack, it's going to go up, reform the carbonyl, and then eject the OET as a substitution mechanism. And then it's Claisen because you're condensing 2 esters together. This next reaction is called a crossed Claisen. So it's called a crossed Claisen because there's only like one option for deprotonating the alpha hydrogen. So like, let's say we were doing this as a reaction. Let's say we had these 2 esters in solution and then we gave them base. So what would happen here? You can deprotonate either here or here. So you're gonna get like a huge mix of products, which is not what you want. So it's crossed Claisen. All you do is basically limit like the possibilities for your product. So there's only one place where we could deprotonate, and it's this carbon. There's no other carbons that have alpha hydrogens in the entire reaction. So we deprotonate there, and then we just go ahead and attack the ester. Same thing happens, OET leaves, and then you just get it substituted. And that's it. That's the crossed Claisen condensation. If you're doing a condensation within the same molecule, so just intramolecularly, it becomes a Dieckmann condensation. So whenever you see this kind of thing, like 2 carbonyls on either end of a long chain, you know it's going to be this kind of condensation. So what you do here, you pick a carbonyl and then deprotonate it. So in this case, it's the same molecule, so I can deprotonate any ester and it's going to be the same product. I deprotonate the alpha carbon, and then I go ahead and attack the other ester in the same molecule. When I attack, the same thing happens, the OET leaves. And then to find the ring, I like to count from the lone pair to the carbonyl. So it's 1. So there's going to be it's going to be a 5-membered ring. So I'm going to draw a pentagon. And then let's say this was carbon 1. On carbon 5, I now have a ketone because the OET left and the new carbon-carbon bond was made. And then on carbon 1, I know I have this ester sticking out of it. And then if it's not symmetrical, Dr. Roche will just ask you for like a possible product. So it would be really silly if he asked you like the order of preference, like which side you would deprotonate on, because there is like not much of a preference. It would probably get a mix of both products. So just pick the one that's like actually possible and reasonable. And it's multiple choice, so he'll make that easy for you. There's no preference. I'm sure there's like, maybe you get slightly major product of like one condensation product versus another, but like there's no set of rules that you had to know for like which carbonyl is going to get deprotonated. Okay, for aldol, if you're condensing ketones and aldehydes together, that's your aldol condensation. Because in the end product, you usually have an aldehyde and then an alcohol somewhere along the way. The exact same thing happens. You have carbonyl with alpha protons, base, and all the base does is deprotonate the alpha carbon. So only one alpha carbon has hydrogens. This one, we can't deprotonate anything else. So what happens, we deprotonate there. There's only one thing to do. We attack the electrophilic carbon, and there's no leaving group in this case. So when we attack, it turns into an alcohol. It doesn't like reform the carbonyl. So we're just gonna add these together. Oh, and then let's just say it gets protonated somehow. So this product happens after the first step. So after the first step of NaOH and H2O, you get this product, which is the aldol addition. I guess just addition product. What happens next in step 2 with H3O plus? H3O plus is going to give you an acid catalyzed dehydration. So the shortcut for this is finding carbons alpha and beta and then just putting a double bond in between them. So in this case, I'm going to locate the carbonyl. So this carbonyl is carbon 1. The next carbon over is carbon alpha. And then the next carbon over is carbon beta. So identify those, and then I'm just like, okay, I'll put a double bond between alpha and beta because I know that's how the reaction ends. Well, I guess another way of thinking about it is that find the alcohol and then the carbon in between the carbonyl and the alcohol. And then like just between the alpha carbon and then the alcohol carbon, and then put a double bond there. Victoria, question?
Yes. So, I mean, you're using aldehydes and ketones that are attached to benzenes. So, there's no more options for like alpha hydrogen. What if it was like a asymmetrical ketone or aldehyde? Like, which side should we attack for the alpha carbon and the alpha hydrogen in that case, if it was like a asymmetrical ketone?
Then you look for thermodynamic or kinetic. So depending on the base you have.
Oh, okay. So if it's like bulky, then we're just gonna go to the side that is less hindered.
Mhm.
Oh, okay.
And then
Awesome.
the other
Thank you.
thing,
Mhm.
this is like the same as the intramolecular one, where it's like
Mhm.
you don't have to know specifically like which of the possible products you're gonna get. Like you just
Mhm.
have to look at the multiple choice and then like
Mhm.
find out which one could have possibly been a product.
Oh, okay. Awesome. Thank you.
So like yeah, you don't need to find like the major one. You just need to find a possible one. So after we get this aldol addition product, we go in with some acid. So what H3O does, the alcohol is going to pronate itself, so it becomes water, becomes a good leaving group. And then while that's happening, we still have alpha protons left. So with these alpha protons, we're going to like form the enolate again. So we're going to send H2O in to do our elimination and then create the enol again. Except we're not creating an enol since this is a leaving group. So when that's going back, this water is leaving. So in our final product, we just have that alpha beta double bond. And then no more alcohol, it left as water. And then this is the final condensation product. And then this is the major product, usually with these reagents. So with these reagents, the first step is like the base catalyzed addition. And then the next step is the acid catalyzed dehydration. And then that gives you the final condensation product. Okay, so there's one giant practice problem at the end and it covers a lot of the chapters. So let's go ahead and do that. The very first one, you have an alkene and then MCPBA. So we know that MCPBA is an epoxidating agent for alkenes. So we're literally just going to slap an epoxide right on top of the alkene. That's it. After that, we have some water and acid. So this is going to be an acid catalyzed opening of the epoxide. If you remember from earlier on this handout, an acid catalyzed opening of the epoxide, you attack with the nucleophile at the more substituted carbon. So in this case, we have a quaternary carbon and then a secondary one here. With an acid, we're going to attack here. So let's say the H2O attacks on that side and then opens up the epoxide like this. So the top alcohol, its stereochemistry is still wedged because it did not get attacked. The bottom carbon that was more substituted, it got attacked by a substitution reaction. So that stereochemistry got inverted. And then this is like how you can tell if the epoxide was opened with an acid or a base. So if you're given the final product and then the beginning epoxide, if in the final product, the stereochemistry of the more substituted carbon flipped, then it was acid catalyzed. If the stereochemistry of the less substituted side flipped, it would be base catalyzed opening. But now we're giving this diol in aldehyde. So an aldehyde plus a diol, if you remember from chapter 16, this is going to give you your cyclic acetal. So for the acetal formations, all we do is get rid of the carbonyl basically. So the carbonyl goes away, and then we create new bonds from each of the oxygens to the carbonyl carbon. So we have our aldehyde there. And then the new bonds between that and the diol. And that's your cyclic acetal. So to break acetals or ketols or whatever, all you do is give it acid and then it goes back to the ketone form or aldehyde form. So if we give this acid, we literally just go back to what we had in the first place. So we're back to acetaldehyde. So if we react acetaldehyde with this big molecule, from this right here, this phosphate ester stuff, the P attached to a bunch of oxygens, we know right away that this is a Horner-Wadsworth-Emmons. So based on that, we know what to look for. We know that we're going to cut off the oxygen of the carbonyl, and then we're going to paste the R group from the phosphonate ester where the oxygen used to be. So I cut off that oxygen, and then right at the end of that double bond, I'm going to paste the green highlighted stuff. So starting from that carbon, literally just paste the exact same thing. And then remember that base is there to activate the ester. So with Wittig and Horner-Wadsworth-Emmons, you usually have a base on the bottom just to signify that like you're activating the illator ester.
So hold on, what is the difference between the Wittig and the Horner-Watson whatever?
There's literally no difference. The only thing is that with Wittig, instead of like this oxygen stuff, like it's replaced with 3 phenols.
Oh, okay. Okay, thank you.
They do the exact same thing. But the thing that he does on exams is that he'll kind of like switch them up. So he'll give you like a Wittig reaction and then ask for like the possible phosphonate ester used to carry out that reaction. It's really stupid, but you just have to read the question carefully and see like if he wants the phosphonate ester or if he wants the illid as the answer. All right, but after we've made this, the ester from the phosphonate or like from the Horner-Wadsworth-Emmons is retained, and now we're giving it dibol. So dibol, all it does, it turns esters into aldehydes. So all we did was change that into an aldehyde. And then we're giving the aldehyde sodium borohydride. Sodium borohydride is a weak reducing agent, so it's capable of turning aldehydes and ketones into alcohols. So it turns aldehydes into primary alcohols, and it turns ketones into secondary alcohols. So now that we have a primary alcohol, we're giving it H2CrO4, which I believe is Jones oxidation. So anytime you have an oxidizing agent with a lot of oxygens, like H2CrO4 or like KMNO4, you know that it's going to be a strong oxidizing agent. So when you have a strong oxidizing agent, you go from primary alcohol to carboxylic acid, and then you go from secondary alcohol to ketone. This is all in the chart I made for chapter 12. It's like a little further up in this handout. But we're starting with a primary alcohol and doing strong oxidation. So I know this is going to go straight to a carboxylic acid. The very last thing, you mean like even a ketone going to carboxylic acid? Or like all oxidizing agents? Ketones can't go to carboxylic acids because there's no leaving group. So like if you're going from a secondary alcohol and you give it an oxidizing agent, like there's nothing to get rid of these methyls down here. So the most you can do is take it to a ketone. But the last step, we're giving it an acid chloride. So when we give a carboxylic acid an acid chloride, you can predict what happens. So we have a nucleophile and it's going to attack an electrophile. So the carbonyl carbon of the acyl chloride is very reactive because it's electrophilic, and chlorine is a pretty good leaving group. So I'm just going to send the OH to go in, attack the carbonyl, and then the Cl is going to leave. So my final product is an acid anhydride. And that is our final product. So we're in the 4 to 5 session now. So if you already signed in, go ahead and sign in again, because like the 3 to 4 and 4 to 5 count as separate sessions. And that's it for this handout. So I'm going to move into the little review set I have for the last 40 minutes or 30 minutes. So for these are multiple choice. So I'm gonna give you a break from hearing my voice a little bit, and I'll give you like a minute or so to like think of an answer, and then you can just send it in chat. The first one
Question.
is signal count. Yeah.
Sorry, this recording is like we're recording this. Where is this gonna be available?
YouTube probably.
Oh, okay, awesome. Tonight maybe or tomorrow?
No, I can do it today.
Oh, okay, awesome. Yeah, that could be great. Thank you.
Oh, isn't there like your exam is tomorrow, isn't it? Or on Friday, something like that.
Yeah, it's Friday.
Yeah, so I might as well just do it now. All right, so the first couple ones are just signal counting. So take a minute and then send me what you think. Will it be on Canvas? Maybe. I don't even remember if I put this link on Canvas. It might be, you can check there, but like everything's on YouTube. Let me send you the link. If you're to get a question and you don't know what to do, for your best guess strategy, I would honestly just like look at each of the options for multiple choice and then like try to think of reasoning behind them. And if like it doesn't make sense, then obviously that's not the answer. So mostly for the reaction questions, like if you have a product and you're like, why is that carbonyl still there? Like where did that carbonyl come from? That makes no sense. There was nothing in the reaction that would possibly like allow that to happen. Then I would just eliminate based off of that. It's like looking at the reagents and kind of recognizing what the reagents do and then comparing that with the answer choices. So I got a couple answers saying 4 for the first one, and yeah, there are 4. So for this, we can cut this molecule in half both ways. So we can cut it this way and then also vertically. There's symmetry on both axes. So now we only need to find the number of signals for one quadrant really. So this methyl up here is 1. This is another one. That's another one. And then one of the benzene carbons is another one. So these are all the unique signals we have. Because of symmetry, there's nothing different than this. Like all of these other signals can be represented by one of these 4. So yeah, there's only 4. Let me skip the next one. Yeah. So what do you think for this one? So you think it's 3 signals and all singlets. So remember your diastereotopic protons. Oh, you mean like the first of the 4? Okay, yeah, that's right. So it is going to be 4 signals and it's going to be 2 singlets and 2 doublets. So the way to do this, remember with alkenes, it's really easy to determine whether the alkene signals are diastereotopic or not. So remember when you have a CH2, these protons are very likely to be diastereotopic, so different signals. The way you can tell that is by cutting the alkene in half and then looking at like the R groups on this side. So if the R groups on this side are asymmetrical, like on top you have a methyl and on the bottom you have all this stuff, that is obviously not symmetrical. So because that's not symmetrical, these 2 protons have different signals. And they're diastereotopic to each other. But for this molecule, we have symmetry. So let's split it down vertically for the symmetry. And then we have our CH3 here. We have our 2 hydrogens coming from the double bond. And then we have our 2 hydrogens down here. So the signals here, the methyl is all 1. because these alkene protons are diastereotopic, they are separate, and then the protons down here are the same because of symmetry. So the pink one and the blue one, those are the two singlets, and then the green and then this one, they're doublets because they are neighbors to each other. So n+1, each of these signals is going to be a doublet. All right, moving on. Let's find a good spectra. Oh, those are all the ones I have. Okay, before we do the spectra, this one, just like I said, you find the terminal alkene. So you find an alkene that ends with CH2, and then you see if they're diastereotopic or not. So the question is asking about protons B and C and the relationship between them. So all I'm gonna do, I'm gonna cut the alkene in half. I see that the two R groups on the other side of the alkene are asymmetrical. So I know they are diastereotopic to each other. So they're different signals and they're also neighbors to each other. Let me find a good spectrum. I think this one should be okay. So take a couple minutes and let me know which molecule you think it is. Another thing, I wouldn't rely on the multiplicity of these spectra too much because it's kind of like all jumbled together. So I wouldn't be like, oh, that's like a quartet, not a triplet. So that doesn't make sense. Don't worry about the multiplicity that much. The last option, close, but it's not it. Yep, it's the fourth one. So the way I start NMR spectra, I look at this spectrum, I mean, obviously, and then I find characteristic peaks. So characteristic peaks, I included that table for the chapter 9 section of the final review, and it includes like basically all the ones that I like looking for first. So right off the bat, I can see that there's this thing in the aromatic region. So if you remember, if I see like this kind of thing where there's two peaks with two integration each, I know it's going to be a para substituted benzene because it's in the aromatic range, and then I have two separate peaks. So I know that the benzene is probably going to be para. So I can tentatively eliminate this molecule. That wasn't so helpful, but at least we kind of got rid of one. Because the rest are all para. The other thing I look for is like the methyls in this case, I see what, like 3 methyl substituents. So I see 3 signals with an integration of 3H. So I know that my thing has 3 methyls on it, which also doesn't really narrow it down. So at this point, like nothing was really helpful based on the spectra and like elimination. So I would just go in and then see which one would make sense. So like over here, like just pick a random signal. So the one down here. So I see it's a methyl and it's not a singlet, it's some kind of triplet. So it's probably next to a CH2. The splitting pattern for a CH3 next to a CH2 is like this. So you get your CH3, it's a triplet, and then your CH2, usually like a multiplet or a quartet. So I'm gonna look for something that has the CH3, CH2 thing going on. So that's literally all of these. That was not very helpful either. Okay. So let's look at the other signals. You have another methyl here, and then another thing here, and another methyl here, and it only really makes sense with this one, mostly looking at the integrations. So it would check out that like this is the 3H methyl, and then these are the CH2 multiplets right next to it. And it's also in the heteroatom region because it's slightly deshielded. So it's at like 2.5, almost 3. So this one is probably the one right next to the nitrogen. And then that checks out with this methyl over here. So cool. And then if I went through all of the other ones, there would be some signals that just wouldn't match. So I don't know, you just take time to count. Yeah, signal counting is a really good way to narrow it down. I'm just really slow and bad at signal counting. So I do like my little elimination thing, and it usually works. In this case, it was not very helpful. But yeah. And you can't go wrong with just like matching signals. All right, let's see. So for chapter 11, yeah, just let me know what you think for the answers of these two. So I got a couple guesses for B and then one for 3. 3 would be correct. So this reaction is your hydroboration oxidation. So if you remember, your hydroboration oxidation is a little funny for 2 reasons. It's anti-Markovnikov and it's also a syn addition. So anti-Mark, meaning the alcohol goes on the less substituted side, and then it's syn, meaning that like the hydrogen and the alcohol are added on the same plane. So yeah, the hydrogen and the alcohol are both wedged or dashed. So for this specific problem, I know that the final product is going to be this. This top carbon is the more substituted one, so I'm going to put the hydrogen here. So if the hydrogen is wedged, then the methyl has to be dashed, and then like vice versa, you get a mix of both. And then the alcohol gets added also wedged or dashed. You get that plus the enantiomer. So syn addition, H and OH on the same plane, and then the methyl gets pushed to like the opposite stereochemistry. So if it started wedged, it ends dashed, and if it started dashed, it ends wedged. So basically for option 3, what's missing here is that dashed hydrogen. And that dashed hydrogen, you have to look for it because it tells you if it was a syn addition or not. So yeah, it's going to be option 3. And then for the bottom one, question?
So for it to be 2, the CH3 would have had to be dashed.
Yeah.
Okay, cool, thank you.
So for this one, did you answer B for this as well? Okay.
Yes.
Yeah, you're right. So it's going to be B for that one too. You know it's B because this was our Markovnikov addition. So the alcohol got added to the more substituted side of the alkene. So we know it was either acid catalyzed hydration or oxymercuration demercuration. It could not have been this one. The issue with A is that acid catalyzed hydration goes through a carbocation intermediate. So the first step after reacting with the acid, you get your Markovnikov cation. And then when you hydrate it, well, before you hydrate it, you can do a methyl shift. So you have a quaternary carbon right here. So you're going to move a methyl down to the carbocation to make a tertiary cation, which is much more stable. Oh, Nicole, the answer was option 3. So with the acid catalyzed hydration, you get that cation, you get that rearrangement, and then you add the alcohol on there. So that would have been the final product. With oxymercuration, demercuration, you don't have a carbocation intermediate, so you don't have any rearrangements, and it just adds like this. I'm gonna skip that one. The methyl shift, yes, the methyl shift is only possible with acid catalyzed. It is the only alcohol synthesis reaction that gives a carbocation intermediate. So that's the only one you can do rearrangements in. For this one, this is epoxidation, and it's asking about cis-2-butene. So cis-butene looks like this, and we're epoxidating that. So which product would it be?
A, maybe?
Yeah, it would be A. So the thing you need to know about epoxides is that the substituents of the alkene, or like the stereochemistry of the alkene, stays the same after epoxidation. So if we start with a cis alkene like this, then the substituents in the end are also going to be cis. If we started with a trans alkene and we epoxidate it, the substituents are also going to be trans. Another way, I hate the way that Dr. Roche writes this, but it's a thing he does. One thing he'll do, instead of making the substituents like dashed or wedged, he'll make the substituents planar, and then he'll make the epoxide dashed or wedged. So for the first one, well, the first one is fine. The epoxide is syn, it is cis, they are both bonds to alcohol are wedged. For the bottom one, you can write it like this. So instead of having like a cis epoxide, or cis bonds to the epoxide, you would draw it like this, where the bonds are trans to each other. And I think this is just like so atrocious because just visualizing it is so hard. So like his idea is that you rotated the stereochemistry of one of those side carbons and then got this as a result. Like one of the bonds to the oxygen became inverted. But just look out for this. So if you start for a transalkene, then this is an answer choice. Very possible that this is the answer. But the answer to this one is just A. All right, let's see. All right, let's do these two. So what do you think for the first question?
B?
Yes, it is reduction of a ketone. And you're right, it is B. So the idea for all chapter 12 reductions, you're basically taking a hydride ion and attacking the carbonyl with it. So this whole thing can be simplified to just like a D minus or like an H minus. So once you have that hydride, it goes in and attacks the carbonyl. So after the attack, you get your D added and then your alkoxide. And then the second step is H2O. It's H2O, not D2O. So when this alkoxide reprotonates itself, it's going to reprotonate itself with a normal hydrogen, not a deuterium. So just keep that general idea of the mechanism in mind. And what do you think about the next one? It's A. You know it's A automatically because we identify the functional groups in the molecule. So we started with a ketone, and then this over here is going to be an ester. And then in the final product, we're left with an alcohol and also an alcohol. So we need to identify a reagent that can reduce both ketones and esters. So what can do that? Lithium aluminum hydride. So there's your answer. And then what reagent can reduce an ester to an aldehyde? Yeah, what reagent does that? Dibol. So if we gave any ester dibol, it cuts off the OR, and you're left with that. Okay. I think this one is good for chapter 13. would PCC or SWERN? PCC or SWERN are weak oxidants, so no. Dibol is a weak reducing. So PCC and SWERN turn alcohols into aldehydes or ketones. It's all in that chart up there for chapter 12.
B.
More stable product. Yep, it's B. So looking at this diagram, the little dip between the two products A and B is your carbocation intermediate. So if you remember, the stuff you're concerned with is like the line of the final product, like the height of that, and also the height of this bump between the carbocation and the final product. So this bump right here represents the activation energy. And then the final line, or like the height of that line, is the potential energy or final energy. So with the activation energy, the higher activation energy it has, like the harder it is to form that product, the more time and energy it takes. So to get the product that's going to form more rapidly, you look for the activation energy that's lower. So you look for the lower bump of the two. Product A forms more rapidly because it has the lower activation energy. And then we're going to look at potential energy. So potential energy tells you the stability of the final product. So the final product that has the lower potential energy is the more stable product. So product A has the lowest potential energy, so it's the most stable, and also the lowest activation energy. So it's the easiest to produce. It forms the most rapidly. So in the answer choices, that is represented by answer choice B. A is the more stable product and it forms more rapidly because it has lower activation energy. For A is wrong because B is the less stable product and then its activation energy is higher. C is wrong. The product that predominates at equilibrium is the thermodynamic product, or the more stable product. So at equilibrium, the more stable one is major. And then intermediate has a short lifetime. Nobody cares about that. So cool. Let's see what else. All right, this is only aromaticity I have. So which of those would not be aromatic? Five. Yep, number 5. So all of these are totally fine. They are 4n+2. They're conjugated, they're planar, they're cyclic. It all works, except there's an issue for number 5. So boron is happy with 3 bonds and it has no lone pairs. So boron acts kind of like a carbocation. It doesn't donate any electrons into the pi system. So for this molecule, there's only 4 pi electrons. And then 4n pi electrons means the molecule is anti-aromatic. And then the rest are totally fine. They all have like 6 pi electrons. All right, let's do this one.
B?
It would be B, yes. And then you know that because this is Friedel-Crafts. So it's Friedel-Crafts alkylation and then acylation. So the important thing here is the order. So one limitation of Friedel-Crafts is that it's really hard, if not impossible, to do Friedel-Crafts with a strong deactivator on it. So this ketone right here that you get from acylating a benzene, that's a strong meta deactivator. That makes it really hard to alkylate afterwards. So knowing that, you can eliminate all the answer choices that acylate first. Because if we acylated first, the second step would not happen. And if it did, it would have just horrible yield. So we get rid of answer choice A and we get rid of answer choice C because they acylate first. What we want to do is alkylate first. And remember, R groups are activators. So if we alkylate first, the benzene is activated and then we can proceed really easily into acylation. All right, I think we have time for one more. Let's do these two. So for the first one, what do you think? No answer key for any of the final review stuff. Yep, this one is going to be number 2. So remember, whenever you have an aldehyde and these reagents, you turn the aldehyde into a carboxylate. The only case where that happens is option 2. And then what about this one? E, either 1 or 2. Yep. So with Wittig, all we have to do is slice the alkene in half and then like make either one the ylid. Like either way is going to work. So to do that, we just separate it and then like add a PPH3 to the R group. So if we took the right side and made that the ylid, then it would be a CH3, then CH2, or CH, bonded to the PPH3. If we took the left side of it and made that the ylid, then you would get this. And that would work as well. Because remember, from the ylid, all we do is take this R group and then transplant it where the oxygen of the carbonyl used to be. So either of these are fine. All right, last question, and then, yeah, we'll be done. This recording will, maybe it'll be on Canvas. It like automatically posts recordings there. I'm not sure if I put the link on Canvas. If the link was on the hybrid Canvas, then yes. But regardless, it'll be on YouTube. And Tiffany is right. It is option 3. So remember, the criteria for racemization is to have a chiral center on the alpha carbon and to also have an alpha hydrogen available at that carbon. So molecule 3 is the only one that has the chiral alpha carbon, and it also has the free hydrogen. The other ones, this is not chiral because you have 2 of the same group. And then over here, it wouldn't do anything. You wouldn't even form the enolate because there's no alpha carbon to get rid of. So that only leaves 3. And it is 5 p.m., so we have to wrap things up here. I'm sorry we didn't get through a lot of the review set, but it's still good practice. But yeah, that's all for me this semester. Thank you all for coming. It was nice. Well, good luck studying for your exam, and then good luck with everything you do in the future. You're gonna do great in everything.